with the introduction, whatever we have now let us go on to the first type of the filter, which is the second order low pass filter. So deliberately I have not added any voice to the previous slide, so which I have already told you in the very first slide itself, right? So now here we shall confine ourselves to the discussion of the second order filters, wherein the rate of attenuation is 40 dB per decade, right? So second order filter. So in the first order filter it is minus 20 dB per decade, right? That is also called the rate of rolling off rate. Okay, that is also to be kept in mind, right? And we will have to look into the second order filters, which are of the Butterworth time, right? We have the different kinds of filters, even based on the flatness of the frequency response, which I did not mention earlier. We have the Butterworth filters, we have the Chebyshev filters, we have the Bessel's filter, we have the elliptical filter, and so on and so forth, right? So among these filters, now we will have to discuss the different types of filters as per your curriculum, only with respect to the Butterworth filters, where you will get the highest possible flatness of the frequency response, right? I'm not going into the other details as far as the Chebyshevs or Bessel's or elliptical filters are concerned, right? So our discussion here would be confined to the Butterworth filter, right? The two second order filters, right? Now, in order to understand the concept of the low pass filter, second order low pass filter, let me start with a small prerequisite, that is the first order low pass filter. Then we will go into the second order low pass filter, and whatever I am showing in these slides, right? So it is basically in this slide, right, is basically a first order low pass filter, right? Do not get confused with the second order low pass filter, which is there to follow in the subsequent slides, right? Now, if you look at the first diagram here, right, the entire diagram can be viewed into two types. One is the passive filter. The second one is the voltage follower, right? A resistance and a parallel combination of the capacitance R1 and C1 that forms the passive filter, right? And which is given to an operational amplifier circuit, basically which is acting as a voltage follower circuit here, right? Now, if you look at the voltage VA, of course VA is not mentioned here. That is the node voltage there, right? Where you have got the junction of R1 and C1, right? So if you look at that voltage VA, by simple voltage division theorem, we have VI into minus JXC1 whole divided by R1 minus JXC1. This is a simple voltage division theorem. And if you take only the magnitude part of VA, we have VI into XC1 divided by under root R1 square plus XC1 square. This is the magnitude part, and if you take the phase angle, it is theta is equals to 90 plus, because of the capacitor, 90 plus tan inverse of XC1 divided by R1, right? And if you look at the output voltage, right, that is the voltage follower, V0 should be equal to VA, because your operational amplifier is simply configured as the voltage follower here, right? And your value of V0 with that will again become V in into XC1 divided by under root R1 square plus XC1 square, right? And the gain here will be no need to mention that it is V0 divided by V in. So you will get XC1 divided by under root R1 square plus XC1 square, right? So this is what is the expression for the gain, and now we should try to see how exactly we have the variation of these XC1 with different frequency ranges. That is where the very application of the low pass filters come into picture, right? Now, if you look at the frequency response, of course it is the hand drawn, right? It is not very neat here, but anyway, you should be able to understand what I have drawn here. you have the frequency, gain versus frequency characteristics, and you have got being a second order filter, you have got the roll off at the rate of minus 40 dB per decade. It's second order filter. So I have shown the diagram for the first order filter. So therefore here the roll off is minus 20 dB per decade, right? So that should be very clear to us. And needless to mention that the cutoff frequency is the frequency when the gain has decreased to a value of 3 dB less than the constant value, right? Now, please look at the explanation there, right? At a lower frequency, right, your Xc1 is much greater than R1. Please look at the diagram here. Since the capacitor is connected in parallel, Xc is equals to 1 over 2 pi Fc, right? So the reactance offered by the capacitor is much less than, much more than that of R1. We have even seen this in the frequency compensation techniques. Am I right? The frequency compensation technique also we have discussed about these things, right? So Xc1 is much larger than R1, and when X1 is much larger than R1. If you look at the expression for the gain on the top, so you will have the EV approximately equal to 1 here. So at low frequency, the circuit does not, offer any attenuation to the signals. So therefore, whatever the signals you have, all the signals get passed through the filter circuit, right? But what happens at the higher frequency? Your Xc1 becomes smaller, right? So once your Xc1 becomes smaller and smaller, finally it results in the increased attenuation, right? So this attenuation starts increasing once the frequency of the signal crosses a certain value, which is called as the cutoff frequency, which you can see from the second diagram, right? So now the roll off starts at a rate of minus 20 dB per decade, right? So that is how you get the frequency response characteristics for the first order low pass filter, wherein you have got only R1 and C1 here, which are basically acting as the components of the passive filter, right? And the voltage follower basically does the function of either passing the signal through the voltage follower or blocking it, depending upon whether your Xc1 is greater than R1 or Xc1 is less than R1. In this way, you have the operation of the first order low pass filter, right? So once the signals, cross certain frequency, then these signals, input signals, are going to be blocked because of the very attenuation offered by the filter circuit. So now, this is the basic prerequisite for you to understand the second order low pass filter, right? Once if you have understood the first order low pass filter, there should not be any difficulty in understanding the second order low pass filter, wherein instead of one R and C ladder, you will be having two R and C ladders, and instead of having the roll off rate at 20 dB per decade, you will be having the roll off rate at 40 dB per decade. In fact, it is minus 40 dB per decade, right? So that we shall see in our next slide now. Okay, fine. Now, with that prerequisite of whatever we have taken for the first order low pass filter, now I have come to the actual content here, that is the second order low pass filter. Please have a careful observation of the circuit as well as the frequency response. Of course, the frequency response is very simple to understand. Now, if you look at the circuit, you have the two ladders here. One is the R1C2 and another is R2C1, as you can see in the diagram, right? So let us have the explanation of the second order low pass filter this way, right? At low frequencies, the Xc1 and Xc2 are much larger than R1 and R2. Again, look at the previous expression what you have taken for the gain, right? So when your Xc1 and Xc2 are much larger than R1 and R2, the output will become almost equal to the input with a gain equal to 1. So therefore, whatever the input signals you have, they they are passed through the filter circuit without any attenuation. So that means the signals of the lower frequency are going to be passed, and you would have the pass band here, right? Now at higher frequency, the effect of C1 and R2, effect of C1, the first ladder, right? The effect of C1 and R2 is to cause the output to roll off at a rate of minus 20 dB per decade, right? And that is not going to end there, and you have got one more ladder, that is R1 and C2, right? So further minus 20 dB per decade attenuation is now due to another ladder, that is R1 C2. So togetherly these two rungs of the ladder, right? That is R1 C2 and R2 C1, right? They result in the total attenuation of minus 40 dB per decade at the higher frequency. What I mean by higher frequency is beyond your cutoff frequency. So now here the roll-off rate is more rapid compared to the first order filter, so that your circuit performance for the given application is going to be very precise, right? This is the only advantage of going with the higher order filter, of course at the expense of having more rungs in this ladder, right? So now after having again the explanation regarding these things I have already given in the first order filter. The similar explanations with respect to the equations and other things hold good here also, but the total attenuation is going to be minus 40 dB per decade. So this is what is the aspect of the second order low pass filter, right? Now how exactly we will have the design and other things for the second order low pass filter, that we shall see in our next slide. Right, now we shall go with the design of the second order low pass filter. Maybe it is a mere repetition of what we are doing here. Recall your frequency compensation circuits, the phase lag networks, right? So there also we had a very similar design. You go back to whatever the notes you have taken earlier and refer to those notes. Anyway, I will repeat the same thing here, right? Now referring to the diagram there, you have the total resistance R1 plus R2, right? So that is the input resistance. These resistances R1 and R2 is evaluated as a single resistance using the very obvious formula, 10% of VB divided by IB max, right? So again, what is IB max and all, right? I am not going to repeat those things again. Several times we have come across this, right? Now let us approximate the design by having R1 equal to R2 and your R3 is equal to R1 plus R2, right? So now we will take R3 equal to R1 plus R2 because we will have to have gain equal to 1 here, right? Now the design of the capacitance, right? So at the cutoff frequency at 3 dB less frequency, you have Xc1 is equals to root 2 R2. Please recall those expressions which we have taken earlier, right? Xc1 is equals to root 2 R2 at cutoff frequency, and you will have C2 is equals to twice C1, right? C2 is equals to 2 times C1 in order to satisfy that particular equation of Xc1 is equals to root 2 into R2 at cutoff frequency. And you have one more equation, that is R1 is equals to root 2 into Xc2 at cutoff frequency. Now this is the relationship between the two rungs of the ladder, that is one is R1 with respect to C2 and second one is C1 with respect to R2. Please refer to the diagram, right? So there is a specific relationship between R1 C2 and C2 R1 in terms of their reactances, capacitive reactances with respect to the resistances R1 and R2 at the cutoff frequency, right? So as long as these two relations hold good, you will have C2 is equals to 2 times C1, right? So now these are the very few steps of the design which are to be followed in the second order Butterworth low pass filter, right? Look at that example, a very simple example, straightforward. Maybe it's a repetition of what we have taken earlier in the frequency compensation methods, right? Design a second order low pass filter to have a cutoff frequency of 1 kilohertz, right? So please visualize the diagram. Frequency response characteristics. You have the gain on x-axis, y-axis, frequency on the x-axis. You have the pass band coming up to the DC to 1 kilohertz, 0 to 1 kilohertz, and beyond 1 kilohertz you have the stop band, right? So that's how your frequency response should be, right? Now, here the solution of the problem is very simple because using 741, though it is not mentioned that you have to use 741, nothing else is mentioned. You will have to use IC 741 here. Therefore, IB max is 500 nanoampere, right? So you will take R1 plus R2. I think you can quickly recall that we get it 140 kilo ohm, right? R1 plus R2 is equal to 140 kilo ohm. So now when you take R1 is equal to R2, then you now individually evaluate the value of R1, R2 and R3. R3 becomes 140 kilo ohm and R1 is equal to R2 becomes 70 kilo ohm each, right? Then the capacitance value, C1, right? XC1 is equal to root 2 R2, so therefore R2 is evaluated. The frequency, cutoff frequency is given, so you can modify this equation. XC1 is equal to root 2 R2 as C1 is equal to 1 divided by 2 pi FC into root 2 R2. So that if you substitute the value of 1 divided by 2 pi, FC is 1000, then root 2 into R2 is 70 kilo ohm. You get approximately 1655 picofarad. Please calculate, have the calculator and the paper with you. Please calculate this value. There may be a small deviation here, and maybe certain approximations are made in taking the value of R2, right? That doesn't make much difference. So once if you have evaluated the value of C1, now you will be able to get the value of C2 easily, right? C2 is equal to twice the value of C1, approximately 3,200 200 picofarad. And if you look at the exact value as per the value of C1, it comes to be 3,310 picofarad, right? Twice 1655. And then I have mentioned that please draw the circuit. Any design is incomplete without drawing the actual circuit and marking all the values, as we have taken several times earlier. Okay? Now with that, this is the simple, the second order low pass filter design. Now let us go on to the next part of it. Maybe this is the high pass filter, right? So we shall move on to the next slide.